chlorides. For the case of chlorides, oxidation state, similarly in the same vein, +1, +3, +4, and then +3, +5, and then +2. In the same way that we described, the one that are in the syllabus are bold, which namely is your sodium chloride, magnesium chloride, aluminum chloride, silicon chloride, and PCl5. So let's take a look at the chemical bonding. In terms of chemical bonding, these two are ionic, and for the rest of the others, they're all simple molecular. Bear in mind that AlCl3 is simple molecular because of the high charge density of Al3+ that attract and distort the large electron cloud of your chloride, so much so that their electron cloud overlap, thereby forming aluminum chloride simple covalent bond. Let's take a look at now the reactions with water, and we look at the pH, we look at the equations in a while's time. In the presence of water, NaCl does dissolve, merely forming ion dipole attraction forces, which is actually a physical reaction, which means you could just evaporate the water and get back your sodium chloride. So the pH is at 7. Next, you get a partial hydrolysis of your magnesium chloride in water. You do get MgOHCl. This is actually a compound that involves a complex ion inside. We'll take a look at a bit with greater details later. That could occur in the presence of water. So the pH is actually about 6.5. Next we have is actually the hydrolysis of aluminum chloride. So when water is limited, not a lot of water, all right, you will end up with actually a white solid, which is namely your aluminum oxide, and you get copious amount of white fumes being formed. That's your hydrogen chloride. However, if you put a lot of water inside, you end up with a complex ion and your hydrochloric acid. We'll take a look at the equations later in a minute's time. The pH of the solutions, 3 to 4. Okay. Then we look at silicon chloride. They could dissolve in water molecules to form silicon dioxide and hydrochloric acid. So the pH is 2 to 3. PCl5 in the same vein, like your aluminum chloride, in limited amount of water, you get POCl3, all right? And then you get the copious amount of white fumes being formed. That's respectively, that is your hydrogen chloride. And in the presence of water, you will produce H3PO4 plus your hydrochloric acid. So the pH is actually 2 to 3 as well. Finally, let's take a look at the states of the chloride. Obviously, for those who are ionic, they're all solid. In the case of Al2Cl6 and your PCl5, they're both solid because of their large electron cloud that they have. And SiCl4 is actually a volatile liquid, similarly to PCl3. Now let's take a look at the equations. For equation writing of dissolving of NaCl, it's just a normal dissolution of your normal salt. If you take a sample of your magnesium chloride, okay, equals magnesium chloride, and you started heating it vigorously, okay, you could actually take a blue litmus paper and you test it. The blue litmus paper will turn red because in this case your hydrogen chloride is released as a gas. Thereafter, if you decide to continue heating it and evaporating all the water, eventually whatever is left would actually be a white solid, and the white solid that you get is in actual fact this compound, all right? And if you continue to heat it, you will continue to produce HCl. That was an exam question that was previously asked at the A level. If you were to take magnesium chloride to dissolve in copious amount of water, the first thing that will happen is that you do form a complex ion. This complex ion behaves as an acid because it's capable of releasing one of the H+ in one of the water molecules to form H3O+. So that's the reason why the pH is 6.5. Aluminum chloride, very similar to this. For the case of aluminum chloride will undergo hydrolysis first, again forming a complex ion, and in the complex ion, one of the H+ will release as an acid, and therefore the pH is 3 to 4. Silicon chloride, as mentioned, dissolve in water to form silicon dioxide, and your hydrochloric acid pH will be between 1 to 3, and PCl3, same thing, will form your H3PO4. And if you remember, we did highlight it is dibasic, and then your hydrochloric acid. In the case of PCl5, you will form H3PO4, which is actually tribasic, and your hydrochloric acid. Bear in mind that all these equations that we have written down here until now, they're all non-redox actually, all right? And obviously, these last two reactions are in fact redox, though not in the syllabus. I think it's good for you to take note. At times, they'll be asked as an unknown compound, and then they'll ask you to do some stoichiometric calculations to determine the formula of sulfur chlorides. Well, let's take a look at some of the possible A-level questions that could be asked. One of the questions that were asked was that silicon chloride could dissolve in water, but CCl4 or carbon tetrachloride is not able to dissolve in water. The reason for that is that silicon is a period 3 element. So since silicon is a period 3 element, it has energetically accessible orbitals in the 3D subshell of the silicon to basically receive the lone pair electron. While in the case of carbon, it's a period 2 element, so therefore it does not have any D subshell. Next reason is because that the bond energy of Si to Cl is lower Then in the case of bond energies to C to Cl, given the fact that carbon has a smaller atomic radius, and therefore because of that, the bond energy would actually be higher. And hence SiCl4 in the presence of water will actually have a fairly low activation energy. Next we'll be looking at why PCl3 could actually hydrolyzes in water to produce your H3PO3 and 3HCl. But in the case of NCl3, when it hydrolyzes in water, you actually produce ammonia. So the reason for that is that phosphorus, again, is a period 3 element, so he has energetically accessible orbitals in the 3D subshell. And unlike in the case of nitrogen, which does not have any low-lying vacant orbitals in the d subshell, because nitrogen is a period 2 element and only has 2 subshell in the outermost electron shell, which is namely your 2s and 2p. And hence, because of this, the water, in actual fact, during the chemical reaction, interact with the Cl instead, and thereby producing ammonia and your HClO. Next, we're looking at A-level questions that involves the complex ion, AlH2O6, 3+. This is something that we mentioned earlier, and you'll typically see when aluminum chloride, for example, dissolve in water to form this complex. Bear in mind that this is actually an acid, as explained, shape is octahedral, and if this complex ion were to neutralize with 3OH-, you will form your aluminum hydroxide and your water molecules, and your aluminum hydroxide formula, typically we write it as AlOH3. The correct formula for the complex is in fact this. So the complex is actually neutral and therefore insoluble in water. By taking the aluminum hydroxide that's produced and we further neutralize it with 3 moles of H+, you will form back the initial complex. Or otherwise, aluminum hydroxide can dissolve in alkaline to form this complex, which is AlOH6 with AlOH6 with actually a 3 negative charge. In the same area that we're going to discuss, we're discussing about amphoteric cation. Al3+, we have covered earlier, which is actually indicated here. So you can see in this example that we have is that we can start off with Al3+ AQ. If you were to add hydroxide, you will form aluminum hydroxide, which is your white precipitate. And if you add more hydroxide, you will actually dissolve to form this colorless complex ion. And if you were to add acid into this complex, what you get, you revert to get your white precipitate, which is aluminum hydroxide. And if excess acid is added, then you will end up with your Al3+ AQ, which is a solution when you first started. So similarly, in the same vein, you will find that reactions that we described applies to Zn2+ and Pp2+. Both of them are amphoteric cation. Correspondingly, they will form your zinc hydroxide, lead-2 hydroxide, and your PbOH4 2- and your zinc OH4 2- as well.